All right, so now in this part of the lesson, we're going to go over a problem that's traditionally known in calculus as the area problem. So what it is that we're trying to find the area underneath a curved line. Up to now in your math classes, you've been able to find like the area of rectangles or polygons, bounded by triangles, that sort of thing. The point is that you really only had techniques to find areas underneath or areas that are bounded by straight line, edges. But in calculus, one of the big motivations was to figure out the area of let's say this shaded area underneath this curved line. It's kind of like in when you're trying to find the volume of a pool. A pool is not like a perfect rectangle or prism. It's curved in 3 dimensions. So the idea is to recognize that this area underneath this curved line can be broken up into a bunch of small rectangles, or a bunch of infinitely thin rectangles. So for example, I could divide this into a rectangle that maybe goes like this, followed by one that maybe over here, and like that, and so forth. See, I can break this area up into subcomponents, basically rectangles. And if I find the area of each of these rectangles and then add them up, wow, it's a crooked line. Add them up, I can get a fairly good approximation of the true area underneath this curve. So let me just do a couple more. Maybe I can go up here. So the idea is if I can find the areas of these rectangles, if I simply using the formulas for rectangle base times height, and then add them all together, that's going to be close to this total shaded area. And the more rectangles, the better the approximation. In here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, like about 12, 13 rectangles. But if I want to be more precise, I can do 20 rectangles or 50 rectangles, 100, 1,000. The more rectangles, the better, as you can understand. But the downside of that is it's going to be more tedious. Takes a longer time. So you gotta see what's actually worth it. Later in the course, we're going to learn a very fast and efficient way to actually figure this area out without having to do all these tedious calculations. But for now, we just want to understand this general principle. So let's go ahead. Let's apply this to an actual function and see what the mathematics behind it looks like, so we can be sure that we understand all the notations and little details involved. So let's look at the area bounded by the common function f of x equals x squared to your parabola. So from 0 to 1, and what we're going to do is break the area into 4 inscribed rectangles. So let me show you what that is. So let's draw a reasonable sketch. I don't know if that's reasonable, but I'll have to do. Here's my function f of x equals x squared. And let's say, the line, this will be the line x is 1. So I want to find, the area here. The area of that shape. Let me do a little better job than that. So the major goal is to get this, area of this, shaded region. You can tell it's curved. So what we're going to, do in this problem is you first, calculate it by using 4 inscribed rectangles. So what that means is the rectangles are going to be completely within this curve. So we're going to need it to first divide it into, equal intervals so that each rectangle has the same width. And since it's, going from 0 to 1, and since it's 4, each rectangle will just be, 0.5, or each rectangle will be 0.25. So let me just break it down here, what it would look like with the interval. So we could say maybe x is 0.5 would be something like that. And maybe x is 0.25 is over, or x is 0.75 over here. And then over here we could have maybe x is 0.25. So we're going to make rectangles partitioned like this. This first rectangle is going to just be essentially a flat line where, these 2 points make up the top corners at the left and the right corner. I'm going to show you why in just a minute. The second rectangle, would look like this. The top left corner would be on the curve, and would go across so that it's something like this. The third rectangle would have, its top left corner over here. Maybe it'd be going out like that. And our fourth rectangle, would be something like this. And keep in mind that this is not drawn to scale, so in probably these 4 rectangles would cover more of the area. But this is a general idea. So we want to find the area of these 4 rectangles. We'll call this one A1, A2, A3, and A4. So the total area of those 4 rectangles, would just be, this would be the sum of A1, A2, A3, and A4. That will give us, the area, within those rectangles. Now, so how do we figure this out? Let's first, we'll go from the left. Now, since this function, goes all the way to the origin, it just so happens that this first rectangle won't have a height because this point here is at 0, 0. If it was at, if it was at like 0, 1 or something, or 0.5, then our first rectangle will actually have a height, but this one wouldn't. It's basically a flat line, coincidentally. Now, the next rectangle, we're going to look at this top left coordinate, and that's going to be at 0.25, comma, remember, since it's on this parabola, you're going to do 0.25 squared, which will give us 0.0625. So let me actually draw this point a little farther out so we don't get it mixed. Let me put it at, so 0.25, and the y coordinate would be 0.0625 because that's 0.25 squared. Because again, it's on the parabola. It's on the equation y equals x squared. Third point, the x coordinate is 0.5, and the y coordinate would be 0.5 squared, because again, it's on the parabola, so 0.5 times 0.5, have a y coordinate of 0.25. And then this last rectangle will have a top left coordinate at 0.75, and then 0.75 squared, which I believe is 0.5625. I'll double check to be sure. Yeah, 0.5625. Okay, so where do we go from here? Well, how he uses that, the area of each rectangle, remember the area of a rectangle in general is, is length times width, length or width times height, however you want to think of it. Length times width or width times height, whatever. So the area of the first rectangle, well, we don't have to really do anything because it's gonna have an area of 0. But let's just let's just go through the math so we know what's going on. The width is 0.25. So A1, you would find the area by taking the width, which is 0.25, and multiplying it by that height, which just happens to be 0. A2 also has a width of 0.25, and the height is given by the y-coordinate of this point here, which is 0.0625. So the area of A2 would be 0.25 times 0.0625. A3 has a width of 0.25, and you probably figured out they all do since we divided this equally. The height is given by the y-coordinate of this point, which is 0.25, so it's actually 0.25 times 0.25. And then to that, we're going to need to add the area of A4, which again has a width of 0.25 and a height of the y value over here, which is 0.5625. So now we just do some basic algebra, multiply those all together and add them. So let's use our calculator to, work this out. 0.25 times 0.0625 plus 0.25 plus and we get a total area of 0.21875. Interesting. Okay, so that's, that's an example of how we can approximate area using inscribed rectangles. But now let's look at how we can approximate this area using 4 circumscribed rectangles. So let's just work on the next page. I'm gonna make this bigger so it's easier to, work with. Again, we have a parabola. Not drawing the scale, but I'm doing my best. With the equation x squared. And we're looking from, the origin from x equals 0, to x equals 1. We're trying to find, again, approximation for this area shaded here, roughly speaking. Okay, so what do you mean by circumscribed rectangles? Well, we're still going to make rectangles of all the same width, so let's divide this, roughly speaking, into 0.25 width. So let's make that 0.5, be 0.75. And that'll be like 0.25. And what we're going to do is then have rectangles where the top right corner is actually on the curve. So the first rectangle will actually go over the graph. It's actually going to have more area than it. It's going to look something like this. So it'll be A1. Let me write A1 in there. We'll call it A2. Will have a top right corner up here. Again, going over the graph. It's going to look something like that. That'll be A2. A3 will be, have its top right corner over here. And A4 will be way up here at the top right corner of the parabola at 1. So here are the circumscribed rectangles. So the technique's the same. We find the area of A1, A2, A3, and A4, add them all together, and that's going to give us an approximation of what the area is underneath this parabola from 0 to 1. So the area let's write out as being equal to A1 plus A2 plus A3 plus A4. Now we use the same general idea, take the area of each rectangle by taking the width and the height, but let's recognize that the height is given by the y-coordinate of the top right point this time. So here, we're looking at this point. For our first rectangle, y-coordinate would be 0.25, x-coordinate would be 0.25, y-coordinate would be 0.25 squared, so 0.0625. For the second rectangle, x-coordinate will be 0.5. Now, where y-coordinate will be 0.5 squared, or 0.25. Okay, and then so for the top right point of A3 will be at 0.75 and then 0.75 squared for the y value, which we found in the previous, part of this problem. Be 0.5625, I believe. Let me check. 0.56. Yep. 0.5625. And then this last point, the top right corner of A4, will be at just 1, 1, which is very simple. Okay, so now let's find the area, just like we did in the previous part for the inscribed rectangles. The area of each rectangle will be the width of each rectangle, which is always 0.25, times the height, which will be the y value of the top right point, the top right corner of each rectangle. So for A1, the width will be 0.25, and the height will be 0.0625. For A2, the width again is 0.25. The height will be the y-coordinate of this point, which is also 0.25. Area of A3 will have a width of 0.25, a height of 0.5625, and an A4 will have a width of 0.25 and a width of 1. Or I'm sorry, a width of 0.25 and a height of 1. Okay, so when we add all this together, we will get, let's see, I got 0.4, what is it? Let me check, make sure I didn't mess. Oh yeah, about 0.46875. 0.46875. Now, since these rectangles go over the shaded region, their total area is more than, the actual region, underneath the curve. So we call this an over approximation, as you would think. And so then the area for the inscribed rectangles would be, we can see it's less than the actual area. So we call this an under approximation. So then when you just think of this, logically, the area would be, between, we would know the area would have to be somewhere between the 0.21875 and the 0.46875. And if we, or actually to, calculate it using calculus, the the exact area we're going to discover will actually be equal to 1/3, or we can say 0.33 repeating. And it is actually very simple to calculate using the techniques that we're going to learn later on in calculus. I could actually figure it out. Like you could probably actually, once you learn it, you could probably do it in less than a minute. So it's going to involve something called the integral, but that's going to be, it's kind of a couple of chapters. So you're going to have to hold on until then. But for now, just make sure you really understand this general idea, because a lot of calculus principles are going to be based off of it. There you go. That's our first lesson.